Good afternoon, everyone. I'm Ianna Osborne. I'm a research software engineer at Princeton and irregular. And I'll be talking to you about awkward arrays in Julia that you can use for your analysis for high-energy physics data analysis. So you are all familiar with awkward arrays, and you know that they can efficiently handle really complex, hierarchical, irregular data, and they are really, really common in high-energy physics, especially. So let's look how we can bridge this to actually use Julia. And actually, before I start with my talk, I would like to shout out for people who actually presented their talks, really fantastic talks showing how awkward arrays are used in various applications. And I'm sorry if I didn't list all of your talks here, and Zoe is going to be talking later today. So please, if you have missed it, just have a look at the talks and join the next talks as well. So we have a package developed in Julia, which is called awkwardarray.jl. And I think it really opens some new possibilities for people to speed up their analysis. So why actually Julia, and why it becomes such a big deal, I think, and what makes Julia so special? I think, first of all, it's speed. So Julia is designed to be fast, and Julia is on par with the such languages like C and Fortran, and it has a really powerful just-in-time compiler that allows you to run your functions at a speed, really performing all these numerical tasks very fast. It's very easy to use, and you have worked with Python, obviously, but it's similar to it's really very intuitive, and so learning this language is not really a big deal. It helps with productivity, and because its ecosystem is actually expanding really fast, and it's very dynamic. And Julia Package Manager is absolutely fantastic. So it's just like it's much better than what we have for Python packages, I think. Just really my personal opinion. The next thing is flexibility, and Julia has multiple dispatch system, and it's really a game changer. So it actually allows functions to behave differently based on their argument types. That makes your code more reusable and generic. Plus, it has metaprogramming, which allows you to write code that writes code, which is really fantastic, I think. It's absolutely, I think, I find fascinating. The community is young, dynamic, and it's open source, so you can actually contribute with ease. And specifically for scientific computing, Julia is a perfect match. Jim gave a talk about why Julia is so a good fit for high-energy physics, and I think I have a link somewhere in this talk. If not, I add it to the slides later. So to conclude, yes, Julia is a good thing, but how our Python community, when you actually invested so much time in using Python, how you can start trying Julia, because you're not going to drop your analysis and just say, oh, I will rewrite everything in Julia. So we give this opportunity to actually share the data, share the structures with awkward arrays. When you have awkward arrays in Julia, in Python, which you are used to, you can also use the same buffers the same data, underlying data, in Julia, and vice versa. So actually, being in Python REPL, you can call Julia, write Julia functions, and operate on awkward arrays, which are either created in Python or in Julia. And why would you do that? Because little by little, you might say, okay, I will use, say, a number to accelerate my function, which is good. Maybe it's not that intuitive. Maybe you will use RData frame, which is allows you to use C++ to accelerate your functions, to operate the data. Awkward Dask, another thing to use with Coffee, what Jason was showing yesterday, also fantastic possibility to accelerate your analysis. Or maybe you would just want to try out another ecosystem, and maybe there is another package you want to try, and write your code in Julia. So why not? So how do we do that? Obviously, we need to install and set up our system, and I will start executing. So we use Python call and Julia call that allow to call Python code from Julia and Julia code from Python, and the interface is pretty symmetric. So I will, there is a notebook attached to the link. Python notebook will be executed. I mean, you can execute it in binder, no problem. There is also a Julia notebook. Unfortunately, the binder will not run it because, but anyway, I will show you. So the usual way Julia call can be installed with pip. Actually, there is Julia Conda package that allows to use Conda, and for installing up unroot, which is a Julia package, we'll use Julia Package Manager. But if you need, for example, to install awkward Python package awkward in the Julia REPL, then you would use Conda, and that actually takes care of everything. In this case, I was using the package manager of Julia to add unroot package. Here, everything was executed, so we already preloaded it. It's already installed. But when you do it the first time, you will see the whole list of messages coming, which packages and which versions are used by unroot, and which versions actually have newer dependency, newer versions, and you may want to consider upgrading. So all the dependencies are defined in your Julia package, and package manager takes care of it. So we are in Python REPL, and we will be using the unroot, which is equivalent to uproot as Python package to read the data. And I use the same data file which you used yesterday in your tutorial with the awkward Dask. And so we just read the file, and we just check whether it's actually, yes, we can see that it's a root file. The printout is different than what you expected from uproot, but obviously you can see that it's a T tree with luminosity block and event and all the stuff. And we can extract events, and it's a lazy reader. So you can see that the events contain multiple information about what we have for 4 leptons here. And we can explore this data by calling the attributes of the event. And you can see that it's a lazy branch, and it's actually a vector of floats. And what is actually important, you can see that it lives on Julia side, because this is a vector, Julia vector. And what we can also check, we can assign Python variables to this branches, and they all will be living on the Julia side. So the next thing, let's look how we can define functions in Python, and how we can run them in Julia. So it's actually very simple. We define the usual Julia function, and we pass it to the Julia main, which we imported earlier. And it just say we need to evaluate it. So now we have the function, which is a Julia function, but we can pass Python variables to it. So this is pretty simple. So let's look at the next step, and we'll take, say, AwkwardArrays. So in Python, the usual import of awkward package, and we need the counterpart of a Julia on the Julia side, the AwkwardArray in Julia, to provide this interoperability between Python and Julia. And let's write a function to convert these unroot lazy branches into AwkwardArray in Julia, and return an AwkwardArray in Python. So in this case, I'm writing again Julia code. I'm saying that I'm using AwkwardArray. This is equivalent to what we have in Python, like import. And then you can see that it's a function, the name, what we pass, and we don't have columns here, and we'll just do the name tuple from all this, because we want to have a record array with fields. And we define the function, and the first time it runs, it will be JIT compiled, and you can see if you run it the second time, it's much faster. So obviously, this is not a showcase that you would want to read one file and then reread it again, but it is show that any function which you define the first time is going to be the warm-up time, and the second time you call it is going to be much faster. And let's check the type of muons, and we can see that the type of muons is actually a high-level array. And let's see, indeed, we have this number of entries here, and the form. And the usual way of accessing the fields in a record array. So this is typical Python. To give an example that what we do in Python to create similar array, I can just do the AKZip and then compare what it gives me. So this step is actually this work is still a work in progress. So your feedback is really important, and it's not like pre-canned solution. There might be some things which are still missing, and maybe some things can be done easier. Say, provided some functions which are give a certain solution. So yes, you can see that it was. So we have muons which are exactly the same. Oh no, not quite the same. So, but okay, so that's something to look at. But still, we have the same records. And how we can use it. So the next step, how we can use it in the data analysis. And I was thinking, okay, you have already learned about the data analysis with coffee, and why don't we just take similar thing and try to convert it to run part of it in Julia? And this is the function which I took from Yason code, find for leptons kernel, which he used in number. And I thought, okay, I'll just take this function and I'll ask ChatGPT to convert it to Julia. And ChatGPT gave me something like that, and pretty close, not runnable, but pretty close. And I will go to actually to Julia now and do the same, because next step, when you write something in as a one string, is very difficult to debug. So we'll do similar thing in Julia. So this is Julia. That's what we did with on the Python side to add unroot to our package, and then we're using it. And we'll open the data. So it's exactly the same. You can see exactly the same output as you have seen from Python REPL, but this is now in Julia. And in this case, we have lazy tree. And I'll just say I'm going to be using awkward array to create my awkward arrays. And this is the same thing you saw in the string. I'm creating a record array with the fields. And in Julia, it's slightly different. So you can see this column PT, this is a symbol. And then we just say we'll just do from iterator, we fill all these fields. And it's pretty fast. We might need some import using Python call, and then when we want to create these 4 muons, we can just say, okay, but we want, instead of using awkward array builder, we define an empty awkward array on Julia's side, and then we populate it by pushing the data into it. So in this case, we need to know what kind of array it's going to be. And we just say, okay, it's a list array of tuples. And when it's created, it has 0 elements, so it's empty. And then we can just say push. And when in this case, we use actually Julia syntax. We just say we push, and then it's a function. We select the slot, and then we say what we push there. So slot selects actually the field in tuple, the slot in the tuple. But actually, for the purpose of this exercise, I will just do a slightly simpler awkward array, which is just list array of primitive arrays. And this is the function, slightly modified function, where I loop over all events, leptons in the events, and just do the matching. And okay, so I'll define the function. It's not quite the same what ChatGPT wrote, but very close, very close. And I'll say, I'll just do the find for leptons for the first 10. And then I display those. So let's switch back to the where was that? Sorry about that. It's just the menus are the menus which I have. Okay, I'll just start again.
If you have to restart the notebook.
No, it's just the menu bar of the Zoom was on the top where I have to select the tabs. I didn't know how to get rid of it. That's
what I was going to say is that you might want to open to some questions now, because I expect that a lot of people are going to have questions about this ability to use Julia in Python and vice versa.
Yes, that's pretty much almost the end. So actually, it's just what are the next steps. I switched back to show that it's exactly the same code, but it's just one string in the on the Python REPL. And yeah, and for the next steps, there is a link to the how to start getting started. What do you need to install in your environment, and obviously feedback and questions are always welcome. And yeah, so please, if you have any questions.
I want to leave this open for everybody. You know, I could ask questions, but I'm perhaps too close to this. So
yes, so
please, yeah, Nikolai.
Thanks a lot. This sounds yeah, very interesting. So I'm thinking a little bit about whether or not this could sort of be become the number on steroids if I want to use awkward arrays in Python and drop to something that I can JIT compile. So, but yeah, I mean, one thing I like about numbers that in principle most of the stuff I can run a number. I also can run as sort of a plain Python code, so it actually makes it quite easy to debug. I can run this in Python, and then I can iteratively check if it's now working with number.jit, and then iteratively replace stuff that doesn't work in number until it finally works. So that's usually how I use it. How would you recommend to use this? Have sort of a Julia REPL open in parallel and develop it there?
No, actually, it's not just about the speed, not about just JIT compilation, but also, for example, if you want to use Julia libraries like unroot or other libraries, maybe combinatorics, maybe something for machine learning. So this opens a way to actually add these fast libraries to your Python projects. Then the other thing, you can use Python tools in Julia workflow. That's another thing. But creating applications within Python or Julia, I think the main goal of this package is just to make sure that HEP community actually tries this really fantastic language. Maybe not at the right time, but it's definitely fit for HEP community. It's easy to learn. So if, for example, in your run analysis, if you want to say, okay, but I don't want to completely discard all my work, but I do want to give a try to Julia, I think this is the way to go.
Okay, yeah. So
maybe it's sensitive. So it's not just like really practical in the sense that, oh yes, number. I really love number. It's yes. If you have Python, you just add a decorator. You go decorator on CUDA. Julia also allows you to run on GPUs on run multi-threaded, so at no extra cost or anything. It just like you just add a variable, say multi-threaded, and just goes multi-threaded. So productivity-wise, what I heard from people at the Julia have workshop, that the students pick it up very quickly. They become very productive. The code is very productive, and obviously multiple dispatch and meta programming. As a software engineer, I really like the idea that how it all works. But yes, if you're in love with number, I think it's yeah, nothing to replace. It's
We would say it's more like really putting getting bigger chunks in like whole packages, like using functionality of unroot or some more complete stuff that some bigger chunk of analysis that I completely then write in Julia, but I can still keep some other stuff that I have written in Python. Not so
yes,
much
for
like
example.
the number thing where I write only a 3-line function then in this.
Yes, definitely. Yes, it's but again, it's just like we are still in experimental phase, and we will see where it goes, because maybe that's not no go to this particular project, and the users say no, we don't need this, we just go completely Julia, which is also valid. But again, having a possibility to, like for example, Jerry Link, he's working on unroot, and he's planning to provide the fast interface, what I showed for conversion of root data to AwkwardArrays straight away. So this will help you with because unroot reads parts of the data and not touching the metadata, so it's sort of like lazy way. And you can see that try in notebook and try to read the same file with uproot and unroot. Maybe you will not get the full data, just in lazy branches. And maybe for your analysis, it's okay. You just run unroot very quickly. You just say I want this form of this array, and then I'll just drop absolutely everything because I know, and I just put it in Dask and build your graph faster. So there are possibilities. Again, it's all experimental, and it's all based on your feedback. Is you say, oh no, I'm not going to use it. That's okay. We'll just drop it. If you say, oh yeah, there is something for me, but I need this feature which is missing. That's also okay.
Yeah, I'll give it a try.
But thank you. Yeah,
Let you know.
Thank you.